welcome again to the new lecture of solar photovoltaics principles, technologies and materials. So, in the last lecture we started talking about the solar cell device parameters. We will further develop on that. Perhaps this is the last lecture on this topic before we move on to the technology. So, I will just do a brief recap first. So, what we saw in the last class was what was the IV curve of a solar cell device, which is typically a fourth quadrant curve. So, you get an IV curve like this. The important parameters are ISC, which is short circuit current, VOC, which is the open circuit current at which the current is equal to 0, and ISC is the current at which voltage is equal to 0. And the important thing about this was that the maximum, the area, the rectangle of maximum area that can be drawn inside the curve determines the maximum power that you can draw out of it. So, correspondingly you have currents and voltages Im and Vm, and the ratio of these gives rise to what we call as fill factor, which is Vm Im divided by VOC into ISC. Another parameter of importance is VOC here, and VOC is nothing but kT by Q into ln of JSC divided by ISC divided by I naught, you can say, plus 1. So, ISC divided by I naught, sorry, this should be like this, yeah, it would be ln of ISC divided by I naught plus 1. You can also write this as JSC divided by J naught, because areas will cancel each other. So, this is okay. And then we looked at the efficiency, that is power conversion efficiency, which is Im Vm divided by incident energy, and this would be equal to VOC ISC into fill factor divided by P incident. Okay. So, the idea for a device engineer is to maximize this fill factor. ISC and VOC are going to be determined by choice of materials. So, once you choose a particular material, there is only an extent to which ISC and VOC can be increased. You cannot obtain because VOC is determined by the band gap of the material, and ISC is also determined by how much a material can produce in terms of current. So, both of these parameters are fixed, maximum limit is fixed for given material. This can be up to 100%, and that it is seldom 100%, but most of the times it is between the range 60 to 80%, and as a device engineer our job is to maximize this fill factor, and that will, so if you can maximize by changing materials VOC and ISC and maximize the fill factor by device engineering, you will obtain high efficiency in the devices. Now, what leads to maximization of these parameters in these devices? Let us see that. So, solar cells are often represented by electrical circuit. Now, ideal solar cell would be where there is no parasitic resistance. So, ideal solar cell would be drawn something like this. Okay. This would be your ideal solar cell. So, you have radiation coming, you give rise to a JSC or ISC. Okay. This would be the dark current, the two opposing currents, and there are no parasitic resistances. So, the only thing that counters ISC is the ID, okay, as a function of bias. Whereas, in reality our solar cell has parasitic resistances, and these resistances are called as series and shunt resistance. So, series resistance is the one which is basically due to resistance in the device. Okay. So, the semiconductor can have high resistivity, which will create resistance to the path of electrons. Shunt resistance on the other hand corresponds to mechanism which leads to leakage of charge. The electrons and holes on the way, they get leaked out or they get lost in some other processes. So, this is represented by what we call as shunt resistance. So, these two parameters are of extreme importance in solar cells. Okay. We will see the effect of these two in case of solar cell devices. So, we look at the effect of these resistances on the performance of. So, we look at the series resistance. So, when you look at the series resistance effect, the series resistance basically affects, if you plot the IV characteristics of a solar cell, this is I, this is V, and the series resistance tends to affect the, so for a good device, series resistance should be 0 or as small as possible, right, whereas shunt resistance on the other hand should be as large as possible, so that you have minimum leakages. These are the two basic concepts. So, now series resistance from this is going to be worked out from the slope of this plot. So, slope of this plot, of course, you can see you have 2 points. This point gives you a slope di by dv. Inverse of this is so inverse of this is the one resistance Rn R1. Again at this point you have, so this is at VOC. Now di by dv inverse is equal to R2 at ISC. So, you can see that as we have said that our ideal curve should be as squarish as possible, which means the current should be nearly flat at ISC and voltage variation should be nearly vertical at VOC. So, if you look at the slope at this point, what is di by dv at this point? Di by dv is equal to 0 at this point. So, which means R1 is infinity. At this point what is, so sorry, R2 is infinity. This is R2. At this point I am saying that this line should be vertical, as vertical as possible. If this line is nearly, if this line is 100% vertical, then the slope at this point will be equal to infinity, which means R1 will be equal to 0. So, the slope corresponding to this point depicts what we call as series resistance. The series resistance for an ideal device should be equal to 0. So, as the device performance changes, when the series resistance changes, let us say if you have series resistance alone that changes, then the behavior is like this. Okay. And this direction would mean that your series resistance is increasing, all right. Series resistance is increasing. At this point when it is vertical, R1 is equal to 0, which is equal to Rs actually, okay. Series resistance will increase because the slope is, so this slope is infinity, this slope is becoming, at this point it is, at this point we are saying that R1 is equal to 0. R1 is equal to 0, you are taking inverse, right. So, the slope is decreasing, which means the resistance is increasing, all right. So, this is the effect of increasing series resistance. If you want to look at the effect of increasing shunt resistance, so the shunt resistance will go in the other way round. So, this is the ideal IV curve you should have, and the shunt resistance variation will be seen here. So, no change in series resistance, but you have change in the shunt resistance. So, this is shunt resistance RSH decreasing, because here the slope is increasing, all right. So, this is what is the effect of and together what they will do is that generally you will see both series and shunt are series is never equal to 0, shunt is never equal to infinity. So, in reality what happens is something like this. So, you will have, so this is the ideal one. So, the ideal one is something like this, okay. The VOC may also change, actually this is the ideal one and this is the practical one, or rather bad device actually. IV. So, for this RSH is equal to infinity and RS is equal to 0. For this RS high and RSH low. So, our job as a device engineer and materials engineer is to decrease the series resistance to 0 and increase the shunt resistance to infinity, so that we get a good IV behavior from these solar cells. So, now if you want to plot the, if you want to do the power analysis in the solar cell. So, if for a solar cell the IV curve is like this, this is IV, and within this we say that we can draw a rectangle whose, so this is, we can say IM, this is VM, correspondingly we have VOC and ISC. So, it is at this point, the, if you now plot, so this point we are saying is the maximum power point or MPP, okay. And the power, if you now plot, the power will go as it will reach a maximum at this point before it goes decreases again. So, this would be the variation of, I can use a different color perhaps, maybe the green one. This power will show a maxima at this point before it decreases. So, this would be the variation of power density of the solar cell, which will achieve a maximum at the MPP point. So, the extracted power of a solar cell is equal to P is equal to V into JV, and efficiency is equal to V into JV divided by PS, and this is maximized when D of JV into V versus dV is equal to 0, right, because it show a maxima here. So, when you make the derivative of power with respect to voltage, that should be 0. So, this is at MPP and this is where you achieve the maximum efficiency or limiting efficiency, which corresponds to the MPP. Okay. So, this is how these two are going to vary. So, if you, so your efficiency will also follow the similar kind of curve at this point. So, your efficiency will be maximum at corresponding to this point. So, essentially the idea is, that is what we said, IM VM divided by P in, and our idea is to increase this product of IM and VM in the solar cell device. Now, let us see a couple of more things relevant to the solar cells, that is, this is what is we did here. So, your incident spectral power density is this E into ISDE, and extracted power is P into JV or IV, if you take the area into consideration, and then power conversion efficiency is V into JV divided by PS. So, you need to be worried about, you need to take into account J and I's little carefully. So, J is current density, I is current, okay, and these two are loosely used in the literature, but make sure as a person who analyzes the efficiencies, he or she must consider the areas carefully and get the units right. So, now we look at the effect of band gap. Efficiency versus band gap of semiconductor, and theoretical calculation suggests that if you plot this efficiency at 10, 20, 30, 40, so this is 10, this is in percentage 10, 20, 30, 40, and let us say band gaps are starting from 0.5, 1.0, 1.5, 2.0 and so on and so forth. So, the maxima in the efficiency is achieved at around these points, and it goes something like this. It is not exactly flat, it has some sort of ripply kind of behavior, and then it goes to nearly, so within this range of 1 to 1.5 these are the, you can say, the optimum band gaps. Of course, there is a whole thermodynamic analysis behind it that you can do to find out the exact band gap, and this is that AM 1.5 G, that is 1 sun. Okay. So, basically we see the conundrum, higher energy gap on one hand gives you small photocurrent because you are going to absorb less number of photons, right. So, if your band gap is higher, the current is going to be smaller, but at the same time the VOC is higher, it also gives rise to higher VOC. So, these two things have to be optimized to get the maximum power output from the solar cell. So, on the other hand, you can see the low EG gives rise to lower VOC. So, lower working voltages are obtained for lower EG, and higher EG will give you higher voltages. So, you will see, for example, silicon which has a band gap of 1.1 volt, it will give you lower VOC, but something like perovskite or organic, where the band gaps could be 1.5 or even higher, they will give you higher VOC. So, for example, in perovskites we get a VOC of the order of 1 volt. So, this is for perovskites, right, whereas for silicon we get a VOC of nearly 0.6 EV approximately, a volt. So, there is a huge difference between the open circuit voltages, and of course, but open circuit voltage is also a function of JSC. So, you can see that this is ISC divided by I naught plus 1. However, since the relationship is logarithmic, the increase is not that rapid in VOC as a function of ISC. And so, the requirements that you want to have for an ideal solar cell device . So, first is any material must have a band gap, which means it must be a semiconductor. So, here silicon has a band gap of 1.1 electron volt, silicon is a indirect band gap semiconductor. Gallium arsenide on the other hand has a band gap of 1.41 electron volt, which is a direct band gap semiconductor. So, gallium arsenide will give you higher VOC as compared to silicon. Second is, all the light of energy above Eg should be absorbed. Okay. And then charge separation, all the electron hole pairs you create, they must all get separated. So, basically you must have exciton dissociation, and then there must be a driving force in the device to make carriers move, okay, to the junctions, to the appropriate ठीक है. And then there should be lossless transport. Which means Rs should be equal to 0 and Rsh should be equal to infinity. That is what you want, okay. And then the load resistance RL should be optimum. I mean, you cannot connect any obnoxiously high load to the solar cell. It should be appropriately matched with the power output of the solar cell device. So, these are certain practical, certain requirements if you want to have a good device, but there are some practical limitations as well. The devices have incomplete light absorption, there is a problem of non-radiative recombination, and there are voltage drops due to resistances. You have shunt resistance, you have series resistance, which lead to voltage drop in the devices, and that is what causes lower efficiency of the devices. All of these lead to lowering of efficiency of devices. So, generally if one does the thermodynamic analysis of we are not going to do this here because it is beyond the purview of this course. So, this leads to maximization of efficiency when eta max is which means all the photons of energies above Eg are absorbed, and if you do this analysis, then maximum efficiency one obtains for single gap devices, which means there is single semiconductor 33.7% at 1 sun, and this band gap is about at about 1.4 eV. So, this is however, if you have infinite number of gaps, which means you are able to use infinite number of materials with infinite number of gaps, which means you are able to absorb every wavelength that comes across, because single gap is going to have a limit, it is not going to be able to absorb anything below the band gap. So, there is going to be cutoff wavelength. But if you have luxury of having infinite number of gaps in a device, then you can increase this efficiency to about 86.8%, okay. So, there is a possibility of having higher efficiency. So, this is the concept behind multi-junction solar cells. Since you can have, so one solar cell will have only one, so this will have one EG, okay, but you can have these multiple layers with different EGs, so that your EG1 is EG2, EG3, so that you absorb the short wavelengths on the top, lower wavelengths, longer wavelengths at the, make a device which is of multiple band gaps, which can give rise to higher efficiencies. Of course, it's a design challenge for materials engineers, but theoretically speaking, one can achieve efficiencies as high as 80%, 85% if you are able to do good device engineering. And as far as I told you earlier also, in the commercial semiconductors, what is important? The absorption coefficient. So, if we plot the absorption coefficient as a function of energy, silicon has a band gap of 1.1. So, silicon is an indirect band gap semiconductor, it shows a behavior something like this, whereas gallium arsenide has a band gap of 1.41. This shows much higher absorption coefficient as compared to silicon. So, this would be something like gallium arsenide and this would be silicon. So, generally absorption coefficients of absorption is better for direct band gap semiconductors as compared to band gap semiconductors. So, this is in general possibility. And if you just plot the efficiencies somewhere as a function of band gap, this is what we have right now. So, if you plot efficiency as a function of band gap, so I made the plot of EV versus eta, it was something like that, okay, and this shows a maximum at around 1.3, 1.4 electron volt. So, your silicon is, so if let us say this is from 0.5 to I do not know 2.5. So, this would be somewhere around, so this is for single junction devices at about 33%. So, your silicon is nowadays silicon is, so this is I do not know, it's about 1.5, 1, 2, 1.5, 1.0. So, silicon is somewhere here, this is silicon. Copper indium selenide is somewhere, it is a little lower than silicon. So, somewhere here is silicon is right now we are at about 24%, 24.7%. This is CIGS, which is at about 19% or so approximately. Cadmium telluride is little higher. So, cadmium telluride gallium arsenide will be somewhere here. So, this would be cadmium telluride, this would be gallium arsenide. Gallium arsenide is at 1.41 EV, CADTEL is little lower, and perovskites have already reached at about 20%. They have higher band gap, more than 1.5 EV. So, perovskites are sitting somewhere here, 20% or so, somewhere here perovskites. And then we have organics. Organics are also roughly in the same band gap range, lower efficiencies though. So, this is where we have organics. I will show you a chart later on in the next class, which can give you a good idea about the devices. So, this sort of completes our discussion on device parameters. We started with the analysis of p-n junction in dark, then we look at p-n junction in light, and then we looked at solar cell device parameters. The idea is to have a as square or rectangular IV curve as possible with minimum parasitic resistances, and we have to optimize the band gap to maximize the VOC. So, we will stop here today.